All right, boys and girls, welcome to our new unit on rocks and minerals. It should be called minerals and rocks because we look at minerals before we get to rocks. Now, I'm just going to be upfront with you guys right off the bat here and just let you know that this first reading is very, very important. You will definitely see this stuff again on future quizzes, and a lot of this is on your test. So you have to know this reading inside and out. Okay, you have to know what a mineral is, how are minerals identified, and how minerals form. All of these, by the way, are key questions that you need to write up at the top there in your notes. As we go through this reading, I'm going to point out things that you need to write in your notes. You can listen to this whole reading first and then go back and do your notes with the PDF, or you can hit pause and complete your notes and then hit play again when you're ready to start. However you want to do this, okay? All right, let's go down to what is a mineral. Look at the two substances in figure 1. On the left hand is a hard chunk of coal. On the right hand are beautiful quartz crystals. Both are solid materials that form beneath Earth's surface, but which is a mineral? Here's coal, here's quartz. Which one do you think is a mineral? Well, we're going to find out. How are minerals identified? A mineral is a naturally occurring solid that can form by inorganic processes and has a crystal structure and a definite chemical composition. This is very important, guys. You have to know this definition. So, 5 things a mineral must have, or 5 things a substance must have to be considered a mineral. It must be naturally occurring, found naturally in nature. It must be solid. It must form by inorganic processes, have a crystal structure, and a definite chemical composition. And you should write that in your notes there. You must know if it's missing one of those 5 things, it is not a mineral. If it's not solid, it's not a mineral. It can be all those other things. It can be naturally occurring, can form inorganically, can have a crystal structure and definite chemical composition, but if it's not solid, then it is not a mineral. For a substance to be a mineral, it must have all 5 of these characteristics. So, is either quartz or coal a mineral? Here again, so here are the 5 things. Naturally occurring. All minerals are substances that are formed by natural processes. Quartz forms naturally as molten material called magma cools and hardens beneath Earth's surface. Coal forms naturally from the remains of plants that are squeezed tightly together. Solid. A mineral is always solid with a definite volume and shape. The particles that make up a solid are packed together very tightly so they cannot move like the particles that make up a solid. Coal and quartz are our solids. Crystal structure. The particles of a mineral line up in a pattern that repeat over and over again. The repeating pattern of a mineral's particles form a solid called a crystal. A crystal has flat sides called faces that meet up sharp edges and corners. The quartz in figure 1 has a crystal structure. In contrast, most coal lacks a crystal structure. Formed by inorganic processes. All minerals must be able to form by inorganic processes. That is, every mineral must be able to form from materials that were not part of living things. Quartz can be found naturally as magma cools. Coal comes only from living things, remained of plants that lived millions of years ago. But some minerals that can form from inorganic processes may also be produced by living things. Definite chemical composition. A mineral has a definite chemical composition. This means that a mineral always contains certain elements in definite proportions. An element is a substance composed of a single kind of atom. Quartz always contains 1 atom of silicon for every 2 atoms of oxygen. The elements in coal can vary over a wide range. So in your notes, it says, for a substance to be a mineral, it must have all 5 of these characteristics. So, naturally occurring, solid, that's what you're writing here in those blanks. Crystal structure is the third one. Formed by inorganic processes is the fourth one. Indefinite chemical composition is the fifth. Excuse me, the fifth one. All right, so coal is not a mineral. Okay, so it's lacking some of the characteristics, several of them. Okay, so quartz is a mineral, however, coal is not. Minerals, compounds, and elements. Almost all minerals are compounds. Okay, here's a blank here. You're going to fill this in. In a compound, two or more elements are combined so that elements no longer have distinct properties. For example, the mineral cinnabar is composed of the elements sulfur and mercury. Sulfur is bright yellow. Mercury is a silvery liquid at room temperature. But cinnabar has solid, shiny red crystals. Different minerals have different combinations of elements. For example, a crystal of quartz has 1 atom of silicon for every 2 atoms of oxygen. This ratio is constant for all varieties of quartz. Each mineral in the garnet group of minerals has 3 atoms of silicon for every 12 atoms of oxygen. But garnets also contain other elements in set ratios. Figure 2 shows one variety of garnet. Some elements occur in nature in pure form and not a part of a compound. Here's your next thing in notes here. Elements such as copper, silver, and gold are also minerals. Almost all pure solid elements are metals. This was in your notes there. Here's a picture of rose quartz. You'll actually get to see that in class. An almandine garnet. This is figure 2. Quartz and the garnet minerals contain the elements silicon and oxygen. At room temperature, pure silicon is a hard, dark gray solid. Oxygen is a colorless gas. All right. This is then your next notes on the back page. It says almost all pure solid elements are metals. So you need to write that in there. Okay. All right. How are minerals identified? Geologists have identified more than 4,000 minerals. Write this in your notes. Each mineral has characteristic properties that can be used to identify it. Here's how we identify minerals. You need to know these because you're going to be using these in a lab coming up next week. Color. Both minerals shown here are the color gold, but only one is the mineral gold. In fact, only a few minerals have their own characteristic color. So which one, A or B, do you think is gold? Go over it in a second. Streak. The streak of a mineral is the color of its powder. So that's what you're writing in your notes there. Although the color of a mineral can vary, its streak does not. However, the streak color and the mineral color are often different. For example, pyrite has a gold color, but its streak is greenish black. There you can see galena, its streak, hematite, its streak, and malachite, its streak. This is a great way to identify minerals. Minerals have a distinct streak. Figure 4. The color of a mineral's streak does not vary. Okay. Luster. Luster is a term used to describe how light is reflected from a mineral's surface. For example, minerals such as galena that contain metals often have a metallic luster. Quartz has a glassy luster. Other terms used to describe luster include earthy, silky, waxy, and pearly. So there you see is metallic. Here's silky. Here's waxy, greasy, or pearly. So talc has a waxy / pearly luster. Malachite has a silky luster, and galena has that metallic luster. And these are in your notes. So luster is the term used to describe how light is reflected from a mineral surface. Hardness. When you want to identify a mineral, one is the most, back to this. Which one do you think is a mineral or is gold? We'll go over that Thursday if you remind me. I'll tell you then. Write down what you think it is. All right, hardness. The most hard. Let's go over this. When you want to identify a mineral, one of the most useful clues to use is a mineral's hardness. In 1812, Austrian, Frederick Mohs, a mineral expert, invented a scale to help identify minerals by how hard they are. The Mohs hardness scale is used to rank the hardness of minerals. The scale assigns a mineral's hardness a ranking from 1 to 10. shown in Figure 6. Hardness can be determined by a scratch test. A mineral can scratch any mineral softer than itself, but can be scratched by any mineral that is harder. For example, suppose you found a deposit of azurite. Azurite is not on the most hardness scale, but you would like to determine its hardness. So you would take a small sample and try to scratch it with talc, gypsum, and calcite. But none of these minerals scratch your sample. Apatite, rated 5 on the scale, doesn't scratch it. Therefore, the hardness of azurite is probably about 4. So all these different things here, how minerals are used, or how we identify minerals, color, streak, luster, the most hardness scale, these are properties that you must know, and we will practice using in upcoming labs. So here it is, most hardness scale, write that in your notes. Is used to rank the hardness of minerals from 1 to 10. 1 being the softest, 10 being the hardest. So here you go. The softest mineral on Earth is talc. Ever heard of talcum powder? That's what makes up baby powder. Talc flakes when scratched by a fingernail. Calcite, a fingernail cannot scratch it, but a copper penny can. Fluorite, a steel knife can scratch it. So fluorite can scratch calcite, this mineral, and talc, but it can't scratch anything above it. Okay. So topaz, it can scratch quartz, but not corundum. So where do you think that would go? Gypsum, a fingernail can easily scratch it. Apatite, a steel knife can scratch it. Diamond, extremely hard, but it can scratch all known common minerals. And quartz, it can scratch feldspar, but not topaz. 1, by the way, is the softest. 10 is the hardest. Talc is the softest mineral on Earth, and diamond is the hardest. Okay, here's the rest of those minerals. That's what I was looking for. So you plug those in here, and we'll go over that and talk about that on Thursday. Okay. So there's diamond. Diamond is 10. It's the hardest mineral on Earth. All right, remember density? We talked a little bit about that. Each mineral has a characteristic density. Recall that density is mass in a given space or mass per unit volume. No matter how large or small the mineral sample is, the density of that mineral remains the same. For example, the density of quartz is 2.6 grams per centimeter cubed. The density of diamond is 3.5 grams per centimeters cubed. To measure density, geologists use a balance to first determine the precise mass of a mineral sample. Then they place the mineral in water to determine how much water the sample displaces. The mineral's density can then be calculated using the following formula. Density equals mass divided by volume. You can compare the density of 2 mineral samples of about the same size. Just pick them up, heft them, or feel their weight in your hands. A sample that feels heavier is probably also denser. All right, crystal structure. Next part of your notes here. The atoms that make up mineral line up in a regular pattern. That's what you're writing. The pattern repeats over and over. The repeating pattern of a mineral's atoms forms a mineral's crystal structure. All the crystals of a mineral have the same crystal structure. Scientists can use crystal structure to identify very small mineral samples. For example, scientists can bounce a powerful beam of particles off very small crystals. Because the atoms that make up minerals line up in a regular pattern, these beams produce distinct patterns of light. As shown in Figure 7, different minerals have different crystals that are shaped differently. Halite crystals are cubic. That is, they are shaped like a cube. You can break a large piece of halite into smaller pieces, but the smaller pieces still contain crystals that form perfect cubes. Geologists classify crystals by the number of faces or sides on the crystals. They also measure the angles at which the faces meet. Okay, so for your notes, you're going to write to this point here. This is your last sentence. All crystals of a mineral have the same crystal structure. So from here to here is what you need to write. Okay? All right. Carrying on here. Cleavage and fracture. You may be familiar with how minerals mica can split apart to form flat sheets. A mineral that splits easily along flat surfaces has the property called cleavage. This is also called breakage. Breakage is cleavage and fracture. Okay, that's a property that we use to identify minerals. Whether the mineral has cleavage depends on how the atoms in the crystals are arranged. The way the atoms are arranged in mica allows it to split easily in one direction. Figure 8 shows cleavage in mica. You can see this. You'll get to see mica in an upcoming lab. Most minerals do not split apart evenly. Instead, they have a characteristic type of fracture. Fracture describes how a mineral looks when it breaks apart in an irregular way. For example, when quartz breaks, it produces curved shell-like surfaces. There's quartz. Cleavage, fracture. So if it breaks apart not on flat surfaces, it has fracture. If it breaks apart along flat surfaces, it has cleavage. So cleavage, fracture. Need to know that. Special properties. So in your notes, fracture describes, you're writing that in there, okay? Special properties. Some minerals can be identified by special properties. Calcite bends light to produce double images, as shown in Figure 9. Other minerals conduct electricity, glow when placed under ultraviolet light, or are magnetic. How do minerals form? On a rock collecting field trip, you find an egg-shaped rock about the size of a football. Later, at a geologic laboratory, you split the rock open. The rock is hollow. Its inside surface sparkles like amethyst crystals, with large amethyst crystals. Amethyst is a type of quartz. You have found a geode, as shown in Figure 10. Write this in your notes. A geode is rounded, hollow rock that is often lined with a mineral crystals. Geologists believe that crystals probably formed inside a geode when water containing dissolved minerals seeped into a crack or hollow in a rock. Slowly, crystallization occurs, lining the inside with large crystals that are often perfectly formed. Crystallization, write this in, is the process by which atoms are arranged to form a material that has a crystal structure. Write this in. In general, minerals can form in three ways. Some minerals form from organic processes. Other minerals can crystallize from materials dissolved in solutions. Finally, many minerals crystallize as magma and lava cool. Organic minerals. All minerals can form by inorganic processes. However, some minerals can form by organic processes. For instance, ocean animals such as clams and corals produce shells with skeletons made out of the mineral calcite. There's a geode. I have some of these geodes, amethyst crystals. We'll show you in class. Minerals from solutions. Sometimes elements and compounds that form minerals can be dissolved in water to form solutions. Write this in. A solution is a mixture in which one substance is dissolved in another. Okay, here's your key icon. Also write this in your notes. When elements and compounds that are dissolved in water leave a solution, crystallization occurs. Minerals can form in this way in bodies of water on their surface, but the huge cell-like crystals shown in Figure 11 formed from a solution of hot water that cooled underground. So minerals formed by evaporation. Some minerals form when solutions evaporate. For example, when the water in salt water evaporates, it leaves behind salt crystals. In a similar way, deposits in the mineral halite formed over millions of years when ancient seas slowly evaporated. Such halite deposits are found in American Southwest and along the Gulf Coast. Gypsum and calcite can also form by evaporation. Sometimes gypsum forms in the shape of a rose. Minerals from hot water solutions. Deep underground, magma can heat water to a high temperature. The water can dissolve the elements and compounds that form minerals. When the hot water solution begins to cool, the elements and compounds leave the solution and crystallize as minerals. For example, quartz can crystallize out of hot water solution. Pure silver is also deposited from a hot water solution. Gold, too, can be deposited in this way. Pure metals can crystallize from hot water solutions underground, often form veins. A vein is a narrow channel or a slab of a mineral that is different from the surrounding rock. Okay. All right. Minerals from magma and lava. Last part of your notes here. Many minerals form from magma and lava. Minerals form as hot magma cools inside the Earth's crust or as lava hardens on the Earth's surface. When these liquids cool to a solid state, they form crystals. The size of the crystals depend on several factors: the rate at which magma cools, the amount of gas that magma contains, and the chemical composition of the magma all affect crystal size. Magma and lava are often rich in oxygen and silicon. Minerals that contain these elements are called silicates. Together, silicates make up the majority of Earth's crust. Minerals from magma. Magma that remains deep below the Earth's surface cools slowly over thousands of years. Slow cooling leads to the formation of large crystals. Quartz, feldspar, tourmaline, and mica are common silicate minerals that form from magma. Minerals from lava. If magma erupts to the surface and becomes lava, the lava will cool quickly. There will be no time for large crystals to form. Instead, small crystals form. Lucite and olivine are silicate minerals that have formed in lava. Very important concept here. You will see this again over and over. Okay? So please just don't tune me out there. Make sure you understand what I'm telling you. All right, so this figure 12, please look at this. Minerals formed from lava, forms on the Earth's surface. They also have, if they cool deep below the Earth, deep below the Earth, as magma cools, they have large crystals. Small crystals on the surface, large crystals in the ground. They form in the ground. Where mineral resources are found. Earth's crust is made up mostly of common rock-forming minerals combined in various types of rocks. Less common minerals are not found evenly throughout the crust. Instead, several processes can concentrate these minerals or bring them together in deposits. An ore is a deposit or valuable mineral contained in rock. Iron ores may contain the iron-bearing minerals pyrite, magnetite, and hematite. Lead ores may contain galena. These ores are mined and the iron or lead is separated from the rock. Graphite and sulfur are sometimes also mined. There you see major mining areas around the world. Boys and girls, as you can tell, this is a lot of information. I encourage you to listen to this several times or read it yourself several times. Study these notes. A lot of the stuff that we covered we'll practice in class, so don't panic. Okay, but you will have to know it. You will have to be able to use these properties to test minerals and identify them. You must know the 5 characteristics a substance must have in order to be considered a mineral. Here they are: naturally occurring, solid, crystal structure, formed by inorganic processes, definite chemical composition. Okay, so thanks for listening. We'll go over this all on Thursday. So make sure you have it done. Have a great rest of your day. Take care.